Okay, so today we will first do a recap on what we cover from Tuesday. And the first thing I need to make sure you are familiar with, I guess, is using pointers in C, right? Because you can use it to implement a lot of like useful data structure, such as linked list, tree. You can use pointer for graph even. And this essentially apply with to any type of collection of items that requires the concept of where's my next item when you want to iterate through a bunch of items. And here's the general guideline. The general guideline is essentially you first declare a struct that consists of whatever you want to store in each item. It can be just one integer, a string, a pair of integer and string, can be an array inside. It can even be an array of pointers that points everywhere if you want to go that weird, right? And then what you want to have next inside the same struct is the pointers or pointers with the plural form to the next set of items. Then you do type def, which basically declare the struct to some name you want it to name to, and this is optional. After you do type def, you declare a pointer that points to the first item. The first thing in the linked list, a root in a tree, the first node in the graph that you want to traverse somewhere inside this structure. Then when you want to add new item, you malloc to append new nodes. We'll play with this in our exercise assignments as well as our midterm. So make sure you do assignment 2 and hopefully finish it before we begin the midterm. Again, the assignment 2 will be out in a day, basically. Tomorrow we will launch assignment 2. And it would be due in a few weeks. I think it's 3 weeks. Typically I would do 2 weeks, but this time because it's potentially there's a midterm in the middle as well, so we'll do 3 weeks. Now let's cover linked list in high level in C because we did a detailed example from the last lecture already. Linked list looks something like this. So let me use pen here. It's whatever value you want to store is inside this node, right? Oh, okay, that's a great question. So there's a question about whether the midterm will be in C or shell script. I would say both. Everything we cover until today, including today's lecture, will be on the midterm. I haven't made the exam yet, so don't ask me what are the things that would go on the midterm. I cannot tell you that literally because I haven't made it. But it would be C and shell script and everything we cover so far, including today's lecture. All right. So for the linked list, right, you have a node that have the value and a pointer that connects this node to the next node. To the next node and so on and so forth, right? You can keep having this thing connecting everything else together, right? And at some point when it's done, you just say this connects to null, which is nothing. It means that you just represent this collection of data that's called a linked list using pointers, right? You point to the next node in the linked list. You can use Q in C as well, and my recommendation usually is I would use an array to implement it because it's actually pretty easy. And if your array doesn't fit anymore, you can just double the size, right? And you can do this once in a while. So you can use an array that looks like this. You put in items, here's the front, and here's the back. Right? You NQ, oh, my bad. You DQ to take something from the front. So it's first in, first out. So when you DQ, you take this thing, take it out of the queue. You NQ in order to put things into your queue. You can also use array to implement a stack that looks like this, right? You push item into your stack, and you can pop this item from the stack. This is last in, first out, right? You can use an array for this structure. Basically, there'll be a top that points to the top part of your stack, right? Where you can push new items into the stack, and now top will point here. You can pop to actually move this out of your stack, which then top will now point to the lower part of your stack. You can use pointers. This looks almost like a linked list, but now you look at the left and the right side of your structure, right? Start from the root in a binary tree. You have the point to the left and a pointer to the right node, which then again contains the value and a pointer to the left and pointer to the right, right? And you can build a binary tree this way using just a struct and a pointer. Any questions before we move on to how to represent the data? All right, so in your questions, type in. I will read that and make sure I address the question. If I'm going too fast, let me know. If I'm going too slow, let me know as well, right? Now we're gonna move on into the concept of how we can talk to a computer. Okay, that sounds really weird, but it is what we are doing, right? When we program something and we want to run the program, you need to be able to tell or command the computer, telling them what to do. Computer, I mean, fundamentally, you cannot really make computer understand our command because it only just deal with electrical signal, right? 0 and 1. Yay, right? So if you look at this electrical signal, which is 0 and 1, this can be represented with binary, right? Using the voltage value, essentially. If you have a high voltage, it's a 1. Low voltage is a 0. And that doesn't have to be the case. Like sometimes in some computer, low voltage means a 1, high voltage means a 0. It depends on how you want to program it. Reading this value can lead to you knowing, right, knowing what is the data and what's the command. So the idea back in the day, the great minds of engineer and scientists who invent computer is, hey, if you can differentiate between high and low voltage, maybe we can represent our human instruction that tell, hey, do an add, do a multiply, do a compare. Use the binary format to program and to encrypt the data. Basically, everything will be in binary, right? And use this binary number as an interface between the assembly code and your computer, right? So today we will talk about how do you represent the data. Basically, if you look at this, program are in binary and data are in binary. This is module 3. We will talk about what is in the program. Today, we will talk about, okay, how do we represent the data? So to represent the data, you need to think of it this way. Everything in the program that you do involve data. You have data as an input, data as an output. You type things into your keyboard. Those are data. It's the different character, right, that represent different number. So if you look at the memory, when you buy the computer, the memory has its own organization. Each program has its own view of the address location. You can malloc, right? You write a program, you play with pointers, and you malloc. Do you actually need to worry where is that pointer? Not really, right? This is managed by the virtual address of the, again, this is in module 3. We'll go into the detail. And when the program is executed, right? This is explained already. You have a program. When you run the program, right? this is what it would look like in your memory. This is your DRAM, right? That you buy, the main memory that you buy. The program will be somewhere in here, as well as your data that you're running, which can grow dynamically depending on the malloc calls, right? So to actually understand our data, we need to first understand what is a word. Can someone to oh, okay. So that's a actually great questions. So the question is about what is a malloc and what is the main process of it? The main process of how to implement malloc. I'm not sure I can cover this in the class today. So I will get, how should I do this? I'll cover this during the review session if that's okay. This is like extra material, and I feel like I probably need like 20 minutes to talk about this, if that's okay. So hopefully that would clear things up. But think of malloc as this. You have DRAM. It can be owned by anyone. When you call malloc, it basically means that, hey, I want this area of DRAM that I want to use. Your computer will say, okay, you can use that part of my DRAM for your program. So that's what malloc is for, to declare that you now own that part of the memory. Right? So hopefully that's clear about what's malloc. Yes, exactly. It's kind of like you book that part of DRAM for your program. So is it more clear? So that's the high level overview. And how it's done, we need 20 more minutes on how the operating system actually track what's free and what's not free. And what can you give to the program and what cannot be given to the program and how to assign the address, right? So regardless of that, let's switch back to the content of this class. In human language, what is a word? So let me ask you this. In human language, what is a word? What does the word mean in human language? And that's a pretty hard question, actually. It's a series of character, right? That means something. Yeah, it's a scribble that explain a concept. It has meaning, right? It's a group of character that has certain meaning. In computer, a word is a unit of data, and hopefully it means something to the computer. These days, when you buy a computer, it will say, hey, it's a 64-bit machine. The 64-bit machine, the term 64-bit means that one word is 64 bits or 8 bytes, right? And in the hardware sense, it doesn't always mean that it has to be always 8 bytes for each instruction, but 64-bit machine just put a restriction that one word is 8 bytes. It's a unit in which the hardware used to transfer the data, right? It's done together as a unit. Basically, I want to transfer the data from DRAM to your CPU, right? You have CPU and DRAM. When you want to access a piece of data, one word is transfer over into your CPU. So that's when you access something, you got the whole word, right? And different architecture can support finer grain. Say, hey, I only need 32 bits. Don't give me 64. It's a waste of power, right? We should go green. I just need 32 bits. That's fine. There are actually some hardware design that offer different granularity. You can operate in 32 bits, 16 bits, 64 bits. You can also implement something, basically an architecture that transfer more than one word. So your modern day computer from DRAM to the cache, which we'll cover in module 3, it's actually more than one word. We'll cover that in a bit, actually, after the midterm is over. Memory address, when you call malloc, you put in what? What's the input to the malloc function? The size, right? Yes, exactly. You put in the size for the malloc and it gives you that exact bytes of free space. So an address typically will point to the first byte of that word. The address that you got, the pointer points to the first byte. So access to the next word will move the address by that many bytes. For example, in a 64-bit machine, you move by 8 bytes. In a 32-bit machine, 4 bytes, right? In C, you can use %p to print the pointer value, or you can use %x to print the hex number. You can use it to help debugging. Trust me, this helps quite a bit. You don't want random decimal number because everything is in the unit of log of something. So %x is a lot easier to process. And there's also this concept of big versus little endian. I need to introduce this concept to you, and there might be questions of like, why the heck there are two formats? It's more like a historical reason. Some machines start with big endian, some machines start with little endian, and because we use multiple types of machines in the computer nowadays, you need to know both and how it works. Byte in the word. Let's say this is your data. So when I say 0x in front of anything, this is a hex number. So let's say that's your data. It's the value of your data, right? How many bytes do I have here? What's the size of my data? It's actually 4. So because this is 1 byte, 1 byte, 1 byte, 1 byte, right? Each number is 4 bits. Each number is in the hexadecimal number, each character is 4 bits. So 1 byte is 8 bits, so it's 2 character. So this is 4 bytes, right? In a big endian machine, such as a Sun machine or like what you use in the network protocol, the least significant bytes correspond to the highest address. I'll show you the example in a bit. Little endian is the reverse of that. Lowest address is the least significant bytes. What is the least significant bytes? Is this bytes. So MSB is most significant bytes. LSB is least significant bytes. Why do we call them least significant bytes? If I change the number from 78 to 79, what's the difference in the value? Can someone tell me? If I say, what's the difference between 1, 2, 3, 4, 5, 6, 7, 8 and 1, 2, 3, 4, 5, 6, 7, 9? What's the difference? 1, right? It's just increment by 1. The change in the number in the LSB bits doesn't make a lot of difference in the value. What about the most significant bits? If I change from 1, 2, 3, 4, 5, 6, 7, 8 into 0, 2, 3, 4, 5, 6, 7, 8, what's the difference? Can someone tell me what's the difference between 1, 2, 3, 4, 5, 6, 7, 8 and 0, 2, 3, 4, 5, 6, 7, 8? Oh, yeah, sure. So there was a question about why 4 bytes again. Just an example here. Basically, I would just assume that this is 4 bytes word. right? Because I don't want to write in too many numbers. It's gonna be just a lot of character on this on the screen. So is it clear? Sorry, it's just an example. Oh, how is that 4 bytes? So how many bits are in 1 byte? 8 bits, correct? Right? 8 bits. 8 bits, not four. For those of you who said four, go get coffee. 8 bits is in 4 bytes. Then, if I just look at this one digit in a hexadecimal number, right? In a hexadecimal number, how many numbers, I guess how many different value for each digit I can represent in a hexadecimal number? I can have 0, 1, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? A, B, C, D, E, F. I can represent 16 different things, right? With me so far? I can represent 16 different things. How many bits do I need for those 16 things? 4 bits, right? 4 bits. I can use 4 bits to encrypt those 16 different things, right? So each digit here is 4 bits. So 2 digits is 8 bits, which is 1 byte. So if you look at this, it's 4 bytes. Okay, so with me so far? Yeah, perfect. So the difference between this number and this number, 1, 2, 3, 4, 5, 6, 7, 8, and 0, 2, 3, 4, 5, 6, 7, 8 is a lot, right? A lot. The value difference is a lot. With me so far? That's why we call those most significant bits, because if you change that bit from 0 to 1, the value change a ton, a lot compared to the least significant bit. All right, with me so far? Basically, is it clear on what's the difference between the most significant bits and the least significant bits? In the big endian, the highest address is the least significant byte. In the little endians, lowest address is the lowest significant byte. So you always look at the LSB, big, high address, little, low address. And I'll show you an example. So some architecture, some machines support both ways. You just need to specify which one are you using so that they know exactly what to do. And here's an example. Let's say I have our value like this, and we store this value at 0x10. Right? With me so far, basically, this is the value and the address is 0x10. Here is what the machine using little endian versus big endian would look like. It starts at 0x10, right? So the value has 4 bytes, right? It's 4 bytes. So we will have to span 0x10, 0x11, 0x12, 0x14. We need 4 bytes for sure, right? In little endian, we say LSB, which correspond to 7, 8, right? This is the LSB. In little endian, we say LSB go to the lowest address. What's the lowest address between 0x10 to 0x13? Which number here is the lowest? Can someone type in the answer just to make sure everyone is with me? What's the lowest value between 10, 11, 12, 13? 10 actually, because just compare the value, right? 10 is lower than 11, lower than 12, lower than 13. I'm looking at the address. I'm looking at this address. I'm not looking at the value. Sorry. I think I know why you said 1, 2. We are looking at just the address. If you just look at the address as 10, 11, 12, and 13, right? The lowest address is 10. the highest address is 13. With me so far, right? Yes, no? That's a long pause here. Are you guys with me or not? Sure. So let me erase these things so that I can redraw. So hopefully it's more clear. All right. I'll use a different color. When we deal with endian, there are only two things you have to worry about: the address, right, and the least significant bytes. So over here, if I have the data value this 1, 2, 3, 4, 5, 6, 7, 8, which bytes is the least significant bytes? Is it 1, 2, or is it 7, 8? It's actually 7, 8. Least significant byte is the one toward the right. Most significant byte is the one toward the left. So this is the LSB, right? Least significant byte. This 1, 2 is actually most significant byte. How do you reason about what's the least significant byte and what's the most significant bytes? Think of it this way. If I change the number, does the value change a lot or does the value change little? For the least significant bytes, if I change the number, let's say from 78 to 80, the value changed by 2, right? The value of x changed by 2. For the most significant bytes, if I change from that number 1, 2 to 0, 2, the value changed quite a bit. It's changed by 2 to the 28, if I'm correct. I might be wrong, by the way, but I think it's 2 to the 28. So is it clear now on how do you identify the least significant byte? Yes, no? Awesome. So that's the first thing we have to care about. Where's the least significant bytes? What's the second thing we have to care about? The address, right? We just want to store our data somewhere. In this example, we assume the address start from 10. Address start from 10. It's 4 bytes long, right? So obviously, these 4 bytes will be at address 10, 11, 12, and 13. Right? With me so far? Yes, no? Basically, we need 4 bytes of empty space for our data. We say the pointer point to 10 because we need 4 bytes. It has to span from 10, 11, 12, and 13. All right. So what's the second thing we should care about? Where's the highest address and where's the lowest address, right? Between 10, 11, 12, and 13, which address is the highest? Is it 10 or is it 13? We just compare the value here. Which address is the highest? Yeah, 13 is the highest, 10 is the lowest, right? With me so far. So what do we say here? If it's big endian, the LSB is at the highest. LSB is what? 78. Where's the highest? 13, right? Highest. That's why you say 7, 8 here. Exactly, yeah. You put 7, 8 there, followed by 5, 6, followed by 3, 4, followed by 1, 2. Little endian is the reverse of that. 7, 8 is at the lowest address, followed by 5, 6, followed by 3, 4, followed by 1, 2. That's it. That's the difference. So is it clear now on what's the difference? So when you see little Indian machine, yeah, I can explain again. So you are with me about lowest versus highest significance, right? The address one. Yeah, sure. Uh, so let me re-explain the address. We have 4 bytes of data. We have 4 bytes of data. Let's say my data start at 0x10. It means that I need 4 slots for it, right? I need 4 slots for my data because each position is 1 byte. So I need 0x10, 0x11, 0x12, 0x13. It's just somewhere in your DRAM from 10, 11, 12, and 13. Are you with me? And we call the lower address, higher number, higher address. So the highest address in here is 10. Oh, my bad. Sorry. The lowest address is 10. The highest address is 13. With me? Okay. So then we just map. If we have big endian, LSB, go to the highest address. What is our LSB? 78. What's the highest address? 13. Right? So 78 is stored here at 13. For big endian, for little endian, LSB, which again is 78, go to the lowest address. So it's go here at 10. So is it clear now? Yes, no. If not, so let me do another example. Let's say this is my value. 0x DEAD. Oh, for some reason we love this particular value. Deadbeef. It's a valid hex number, right? Then let's say it's stored, so ampersand x in C is the address of x is at 0x34, right? This is the LSB, this is the MSB, right? With me so far, basically this is our address. We will just have to put the word dead beef somewhere here. Little Endian, what do we do? What does little Endian do? We put LSB at the lowest, right? At the low bit, little, you go down. So LSB, EF is here. BE, which is the next word, right? This BE is here. AD and DE. All right. So big Endian will do this. Same address, right? But we put the least significant bit at the end because it's big, right? So LSB at high address. So EF followed by BE, followed by AD, followed by DE. All right. So clear? Yeah, it's the invert of each other, essentially, for big and little Indian. There's a wait what comment in the chat. So is it clear for you? Or should I any part that's not clear here? Okay, long pause. If it's still not clear, let me know when we do a break then. We'll do a break in about like 25 minutes, I think, once we cover some of the data types. Right, so let me move on to the next set of topics. In C language, there are multiple data types. So let's start with the simplest thing, character. How to represent a character. Typically, we can use ASCII number for that, right? What's that? ASCII is a map of a value between 0 and 255 with a character. For example, the capital A is 65. Number 13 mean new line. How many bytes do you need per character? In this case, it's cover 0 to 255, right? So it means that in total, 256 different number. So you need log 2 of 256. What's log 2 of 256? So you need log 2 of 256 bits. Equal how many bytes? How big is one character? How many bytes? One byte. Okay. One byte. One byte. 8 bits. This is 8 bits, which is 1 byte. No, you're correct. It's 8 bits, right? And it's if you convert 8 bits to bytes, it's 1 byte. All right, so let me tell you a trick on how to convert between binary, back and forth between binary and hex. So let's say I have a number called 0x beef because I'm hungry. I'm kind of hungry. So let's say I want to convert beef to a binary number. What is that number? How would I do it? The way I would approach this is I would do each character at a time. Why does it make sense? I just told you, right? One character in a hex number is 4 bits. It's 4 bits. What is the letter B? What's the number for letter B in binary? A is 10, B is 11, right? What's 11 is 1011, right? What is E? 1110. F is 1111. Why can I tell E is 1110? I know F is 1111, right? This is pretty common. F is like max of the number, so it's 1111. E is one below that, so it's 1110. So these number in hexadecimal, beef is 1011, 1110, 1110, and 1111. In binary, whenever I have this, it means it's binary number. Whenever I have this, it means I'm looking at a hex number, hexadecimal. All right, with me so far? Converting between hexadecimal to binary. How do I revert back? So let's say I have this pattern. 1111110100011. What do you mean by flop the bit from 0 to 1? Now I'm confused. Is that a question? Sorry, that was the private chat. I'm trying to understand if that's a question. No, but what's that for? I guess I'm kind of lost here. Changing the bit. Oh, connection abort from our server. So I'm not sure. I'm still not sure. I quite exactly know what you mean. So are you talking about changing from binary to hexadecimal? Okay, regardless, let me tell you how to change from binary to hexadecimal, right? So let's say I have this bits. What I will do is I will break these letters down into a group of 4, right? I'll just break it to a group of 4. What is 1011? We just did it. That's B, right? Again, so that's B. 0111 is 7. 1010, that's 10. So 10 is A. 1111 is F, right? 1 is 1. So this corresponds to 0x1F A7BB. All right. Any questions so far? Any questions so far? So this is how you can convert between binary and hexadecimal and back. To represent a string is essentially in C language, it's an array of character. A character is encoded in ASCII format, right? Oh, okay, I got your point. Okay, yeah, sure. So a null value is it will be put at the end of your string. Basically, when you have a string such as FilePro, which is the name of this class in the previous curriculum. Actually, it's from the 58 curriculum. It's the previous 2 curriculum. We call this class file processing. So if you want to have a string named file pro, it will actually be an array that have the letter F, I, L, E, P, R, O, followed by one more value, which is the value 0. How about an integer? Integer can be represented using a binary value, right? How many bytes required depends on the maximum and minimum range. In ANSI, this is like an old version of C. ANSI is a textbook version of C that we will use in most of the like introductory class. In our class, we use a more modern version of C. So integer is now, I think, 4 bytes, right? So in ANSI C, short int is 2 bytes, integer is 2 bytes, long int is 4 bytes, long is 8 bytes. You might have noticed this number is different now. Integer is bigger, so the size of each data type can change all the time based on the architecture, basically based on the processor that you're using. Each one has its own definition. So you want to use the keyword size of over here to make sure you're safe on what's the size of each of these data types. All right. You can also have signed versus unsigned version of your data as well. Integer can be positive or negative. Unsigned, pretty clear. You just have a positive number starting from 0 to a max value of that. You convert binary to decimal to get the value, right? A signed number will be represented using what we call a 2's complement format. So let's say we have let's assume 1 byte character, right? 1 byte. Give me any random 1 byte. Can someone give me any random 1 byte? That's half a byte. Give me 4 more bits. Okay, so that's the byte you're suggesting. So this unsigned will equal, right? What's the value of this in the unsigned realm, right? In the unsigned world, what do we do? It's 1 multiplied by 2 to the 7, right? Plus 1 multiplied by 2 to the 6, plus 1 multiplied by 2 to the 5, plus 1 multiplied by 2 to the 4, plus 0 multiplied by 2 to the 3, plus 1 multiplied by 2 to the 2, plus 0 multiplied by 2 to the 1, plus 1 multiplied by 2 to the 0. So that's the value of the unsigned character 11110101. Everyone with me? if I do my math correctly, I think this is 249. Right? So that's 249 in unsigned world. In a signed world, what is this value? It's exactly everything is the same, but your most significant bit now is a negative value. So what does it mean? The most significant bit is this one, right? So instead of 2 to the 7, you now have negative 2 to the 7 plus 2 to the 6 plus 2 to the 5 plus 2 to the 4 plus 0 times 2 to the 3, so that's 0, plus 2 to the 2 plus 0 times 2 to the 1, that's also 0, plus 2 to the 2 to the 0. That's the value of the same exact bit pattern, this value, in a signed character, right? Whenever you have a signed number, the MSB becomes the negative value. The rest is the same. So what is this? This is negative 128 plus 64 plus 32 plus 16 plus 4 plus 1. Whatever that value is, right? So what's this value? I believe this is negative 5. Can someone confirm that? I'm not sure. I think it's negative 5. Is this the same as the... That's a great question. So that's a question that says, is this the same as the negation, the flip of the bit? Close enough. We'll cover this a bit in a few slides actually, but we will develop the notion that negative n equals not n plus 1. Oh, it's negative 11? Really? Oh, okay, maybe I'm wrong. Yeah, but okay. All right, thank you. Oh, but you got negative 5. Yeah, I think it's negative 5. I'm not sure. I'm pretty sure it's negative 5. Like negative 11 is too far from the range of possibility. So maybe I did something wrong, but it should roughly this pattern, this, if I just look at that, right, and if I know that negative n is not n plus 1, right, if I do not n is 6 minus 1, that's 5, so this should be negative 5. That's how I cheated and I got negative 5. So maybe I'm doing something wrong here. But I think you got the message. The next thing I want to let you know is for constant, right? For constant, you can add the capital U at the end to make sure when you type in constant, treat that number as unsigned. Treat that number as unsigned. Why do we have to be careful? Because you most of the time you want to make sure you don't mix between the two numbers. The expression of both signed and unsigned can be mixed if you just do a plus b like this, right? If you add those two and one of them is signed, the other one is unsigned, the signed value is cast as unsigned. Generally, which it means that you want to make sure you cast your data type manually, otherwise have fun debugging, basically. be careful when you add the two number. Most of the time it won't be buggy, but sometimes it might. Extension versus truncation. When you have a negative sign number for the extension, if you want to cast like a short int a into int of b, right? This is extension a. Like what you want to do, b equals a. That's good, right? You want to put whatever value a is into b. Unsigned, everything looks the same. Easy, right? Sign number, sign negative number. What will happen is we extend once to the MSB. So let's say A is B. This is 1 byte, right? And let's say B is 2 bytes long. B would become 111111111111000. This part goes to here, and then you extend with a bunch of ones. It will work, and the number will translate to the exact same number. It will have the exact same value. If you convert, say, -10 into a bigger data type, it will still be -10. Truncation is different. Truncation, let's say you have A and B like this, but you do A equal B, right? It will drop the most significant bits. So value can change, right? Value can change. Let's say you want to assign the value 101011, something like this. You want to assign this into 1 byte, what you will get is just this. This part will be gone because there's no space for them. It will actually literally drop that part. So value can change. In summary, you can extend things from short int to int to long int, but you should not truncate. Essentially, it means that you should not be careful, or should I put it? Be careful if you want to convert an integer into short int, long integer into int. Value can change. All right. The next thing I need to tell you how it works is the floating point number, right? A floating point number, if you look at binary data, it consists of 3 parts. This is not on the midterm. Just for the sake of your sanity, we are not going to ask you to convert bits into a floating point format because it involves a lot of multiplication and power. Want to make sure my students is seen, so no questions related to floating point number, but I want to teach you how it works. There are 3 pieces of information. One sign bit, number of exponent bits, and number of mantissa bits. In a 32-bit floating point format, so the one that takes 4 bytes, this is 4-byte float. It would be treated the same way. This format is called IEEE 752. IEEE is an engineering organization that occasionally they will come out with the technical specification for things. In this case, they say floating point. Every computer will understand that these bits mean what, right? This particular format has, out of the 32 bits, there'll be 8 exponent bit, 32 mantissa bit. I'll explain how things work in a bit, right? So one at a time. I'll make sure you understand, but one at a time. The exponent bit, I'll call them E. The mantissa bit, I'll call them N. The way it works is for the exponent part, we convert the value directly from binary. So let's say the exponent bit is 0, 1, 1, 1, 1, 1, 1. This corresponds to 127, right? We'll treat it as E equal 127. We plug this into this equation. This equation is the value of your floating point number. For the sign bit, if it's 1, it's negative number. 0, positive number. That's easy. Exponent, convert the binary into a number. That number is e, plug e into here. So that part is also hopefully now clear, right? In this case, it's 0, 1, 1, 1, 1, 1, 1, 1. That's 127. So e becomes 127. So in this example, we are talking about 2 to the 0. Basically, we're talking about 2 to the 0. So you multiply by 1. Let's talk about a little bit more annoying part, the m part, right? The m part. How does it work? M is 1 plus sum of this. 1 plus, it can be these 2 to the negative I, right? This is 1/2, 1/4, 1/8, 1/16, blah, 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 right? So the way it works is, let's say your mantissa bit is 10111. Let's just assume it only have 5 bits, right? Let's assume it only have 5 bits. The first one means that I'm gonna add 1/2 to it, like this. 0 means that I'm gonna have 0 multiplied by 1/4. 1 again means that I'm gonna have 1 multiplied by 1/8. 1 here means that I'm gonna have 1 multiplied by 1/16 plus 1 multiplied by 1/32. So that's the m equals m. You plug that in this equation, and that's your value. That's the value of your floating point. And here's some more examples to make it hopefully more clear. So let's say this is your floating point. Let's assume that this is your exponent bit, and because I don't want to write something too long, this is your mantissa bit. What's the value of this floating point? This tells me it's a positive number, right? This tells me is exponent is, what is it? 8 plus 4 plus 2, so that's 14, right? What's m? Over here is 1 plus 1/2 plus 1/4, and we skip 1/8, 1/16, 132, 164, and we skip 128, so we have 1/256. So that's mantissa bits multiplied by 2 to the 14 minus 127. So that's the value of our floating point. It will be exactly as that, right? All right. Any questions so far before we take a break? We will do a break here before we go to logical operation in C, which is kind of like the last topic before the midterm, like literally the last thing before the midterm. So let's do a break. We'll meet again at 3:10. We'll do like roughly 6 minutes break. All right. In the meantime, I'll actually I need to get some water because my throat is really dry right now. But if you have questions, type it in. I'll come back as soon as possible to address your question, and we resume the class. Is that okay? Okay. All right. Okay, so you got permission. Wait, is this a Mac or a Windows computer? It's on a Mac, and you got permission. So permission denied typically means that you either have the wrong username and password, uh, which is kind of weird, or you like somehow put in a wrong like location. Uh, what's the best way to do this? So I think P. Cliff, our TA, has his office hour on Friday. You just need to go to the Google form and let him know, uh, so that tomorrow he can come and kind of like get you through the problems. Because I'm not sure I have time tomorrow to kind of or tonight to help on that. I'll try. Basically, I'll try to come tonight, but for sure that's office hour slot from our TA tomorrow. So maybe check with him. I'm sure that's like a easy way to fix this. Uh, there's another question about how to do the extending negative sign number. So let me give that example. So, okay, so let's say we have a negative number. Let me do this. So we have this number, right? And it's a negative number. So what is this number? It's negative 127, right? Plus 64 plus 32. That is 63. That's 31. That's 31. I mean, negative 31, right? If I say I want to put this number in a 2 bytes data, right? 2 bytes data. What do we have to do here? In C, in C, what this is what will happen. It would extend 6, no, 8 more. My bad. That's too many. So this is our original number. It would extend, I'll use a different ink color to make it clear. It would extend this once, right? What time do I usually go on Discord? Whenever I have free time that doesn't exist this week. Sorry, but you typically, whenever I have free time, I try to check in Discord once in a while. This week my life is like miserable. In terms of like deadline. So I'm sorry. I'll try. I'll try my best to go to Discord. How about like 10:30 today? Let me put that on my calendar, and 10:30 I'll try to be on Discord. Okay, so I'll try. Uh, at least it's on my calendar, so it will actually pop up at 10:30, and I'll go there. Uh, which is obvious hour again. I'm actually aiming toward like 4 o'clock on Tuesday, if that works for you. I haven't announced it yet, but it's likely that it'll be 4 o'clock on Tuesday. So, okay, extending the bets, right? This number will equal to negative 31 as well. It actually will. The reason why it works is these become the negative something, right? Everything else you add here is a positive number, including this one. These positive number, when you add it to negative n, which are now bigger, will go back to negative 127. It will actually becomes negative 127. So that's why this works. negative 128. Okay, sorry, one bug here. Negative 128, and this should be negative 32. That's why we need to check our answer. I make mistakes here. So it's negative 32. All right. So this is how you can use sign extended when you extend the number from say 1 byte to 2 bytes. It applies through 2 to 4 bytes to any number of bytes. All right. So before we leave today, this is the last concept, and I think we'll take about like 30 minutes, 25 to 30 minutes to cover. It's called Boolean algebra. And the reason why we spend a little bit more time compared to previous semesters, my understanding is these days there's no digital design class required for you anymore, I think. So I would like to make sure you know some basic like logic, essentially. So when you look at logic, right, there's true and there's false. So in computer science or in your machine, actually, the value 0 is represented as false, 1 is true. And you can actually now build a truth table, right? What is a truth table? A truth table is a table that represent all possible results of a Boolean algebra. For example, right? If I want to build a truth table for A and B, what will the table look like? So this is A, this is B, this is A and B. If A is true, B is true, A and B is true, A is true, B false, A and B is false. If A is false, B is true, this is false, 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 false. Right? False, not E. We call this thing a truth table. Right? So there's a comment about logical operation. So logical operation is not exactly, it doesn't require memory or what, but it's one of the operations that's easiest to do in computer. And or not X or NAND nor these thing is quick. Basically, if you want to apply this operation, it's quick. It's even faster than an add or subtract. Add or subtract consists of multiple NAND or NOR or AND or NOT, like a bunch of these things. Right. So and multiply now is a bunch of adds, right? A bunch of add and shift. So you can imagine how complexity of each operation grow. Logical operation is one of the simplest operation you can do in your computer, right? And the truth table is basically you expand all the possible value of the inputs and the results of your logical operation. For example, truth table for A and B is what I show you. A or B will be true, 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 false, true, true, because everything or the other, if there's one true, it becomes true, right? So for or, if you have true and true, that's true. True and false, that's also true. False and true, that's also true. And false is false, right? Not if you have true, that becomes a false. False becomes a true. XOR, if you have true and true, you have false. Basically, XOR, if it's the same thing, that's false. If it's different, that's true. False and true, true, true and false, true, false, and false is false. That's why it's called exclusive OR. Is the exclusive, you only want one of them to be true. If both of them are true, that becomes a false. NAND, this is not and. This is not or. All right. So with this, you can do what we call Boolean algebra. Boolean algebra is basically we group bits into a vector. Let's say, what's the value 5 in binary? What's 5 in binary? 0, 1, 0, 1, right? 6 in binary is 0, 1, 1, 0, right? What is 5 and 6? The way we do this is we will do a pairwise AND. So this thing is group. What's 1 and 0? What's 1 and 0? 0. What is 0 and 1? 0. What's 1 and 1? 1. 0 and 0 is 0. Oh, 0, 0, 0. So 5 and 6 equal what? What is 0, 1, 0, 0? 4. Yeah. So 5 and 6 is 4, which is not the same as 5 and 6, right? So what is 5 and 6? This means we treat 5 as a true or false. This is true. This is true. So 5 and 6 is true, which is 1. Right? So if you do 5 and 6, you get 1. So operations is now done on the bit vector as I show here, right here. This is how the operation is done. And all bits operations that I just listed earlier are available in C. Not and or XOR, right shift, left shift. So this is not and or XOR shift, right? And as I said earlier, this is different from the logical version of this. And yes, so there's a comment saying if you just put a number, if your if else condition, for example, if 1, it will not cause a bug because 1 is true. This is the same as you said if true. But the keyword true, it doesn't exist in C. In C language. So if you want to say if true, if bracket 1, I'm not sure why you would want to do that. That's weird, by the way. But you can say if X, and X can be any number. Boolean is not supported in C. So if you want to use a Boolean, just use integer character or anything, any non-zero, right? 0 is false, non-zero is true. So in C language, 0 means false, non-zero means true. There's no Boolean for you to use. All right? So what you can do, now that you know there's a bit vector, right? So I will give you one example that I would implement intersection and union as a set operation, right? I can use bit vector as a set, right? Basically, here's a trick. I would say bit value ones mean that number is present, 0 means not present. So let's say I have an array, right? Not an array, but basically this is, give me a set that consists of number between 0 and 8. Can someone give me a set that just consists of number between 0 and 8 so that we don't have to write something too long? I'll just throw in random number then. 1, 5, 7, 8. So let's say that's my set. And say I want to do this union between this set and 0, 3, 8. Right? So what's the result of this? If I do the union, match definition, I will get 0, 1, 3, 5, 7, 8. Right? One trick I can do is if I know the maximum value of my set is not that high, this is 8, right? The maximum value here is 8. So I will represent this with a number. I'll just use a bit vector, right? This is 0th bit, 1 bit, 2 bit, the 3rd bit, 4th bit, 5th bit, 6th bit, 7 bits, 8 bits, 9 bits. And let's say I want to use a 2-byte number, so it extends to 16, 15, right? In this case, 10, 11, 12, 13, 14, and 15, right? So that's my number. Is 2 bytes long, 16 bits long. Every time I have a number in my set, for example, if I want to represent this set, I will put in the value 1 on that number. So that's 1, right? I will put 1 here. It's 5, 7, and 8. The rest are 0. 0 means that there's not this number in the set. How about this set? This set would be, right? Draw hopefully similar array of bits. So we have 1 at 0, 1 at 3, and 1 at 8. If I want to do a union, I perform an OR. Right? If I want to do the intersect, I would do an AND. So this is union. This is the section. Right? And I'll know the result because the bit vector would tell me if I have the number 1, it means that number is there in my set. So as I show here, intersection is AND, union is OR. You can use XOR for symmetric difference. Basically, if that's the number there, it becomes a 0. But if there's one number in one set, but it's not in the other set, it becomes a 1. And also do a complement using a negate. So that's one example that you can use in order to use a number to represent a set, right? This is much more compact in compared to maintaining this whole set, right? I just use 2 integer. That's it. I can use logical shift or arithmetic shift for multiply as well. I'm going to show you in a few more slides, but shifting, there's 2 versions. There's logical shift, which means I'm just shift the raw bit vector. Arithmetic shift will preserve the MSB. So let's say I have this number right here. Arithmetic shift right by 5 will shift everything here by 5 bits to the right. So this is gone, this is gone, this is gone, 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 right? So you have 1, 1, 1, and it preserves the MSB, so it looks at this more significant bits. If it's 1, you can skip. Add 1 to make sure it's 8 bits again. If the number is 0, 1, 1, 0, 1, shift right by 5, and gone, 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 gone. So you have 0, 1, 1, and because this number is 0, you're going to extend this 0. All right, so that's how shifting works. So you can then do more complex operation using logical operation. Here's the first example. Let's say I have a number n. I want to have negative n. This is negation, right? I just want, oh yeah, I can go back. Sorry. Yes? Oh, okay. So I guess you just want to take notes, right? Okay, sure, yeah. So basically shifting is just you move the bits, the position of the bits left and right based on the number you want to shift. And now we're just going to teach you different tricks you can do. Negation. Let's say you have a number n. and you want to compute negative n, right? You want to compute negative n. The way this works, as we described earlier, right? This is actually simple. You can do not n plus 1. This is negative n. All right. Why does this work with the 2's complement format? Okay. Why does this work with the 2 complements format? Basically, you shift, let's say you look at this number, right? This is 2 to the negative 7. I mean, my bad. Negative 2 to the 7 plus 2 to the 6 plus 2 to the 5 plus 2 to the, what's it? 2 plus 2 to the 1 plus 2 to the 0. So that's our number. If you flip out the bits, what will you get? Right? What will you get? You will get this number and this number. So that's 2 to the 4 plus 2 to the 3 plus 1. Right? That's essentially all the missing number. To make sure it matches up to the negative 2 to the 7, you add 1 to it to make sure you go over that boundary, it becomes the negative version of that number. What is this value? Right? That is 16 plus, what's the root 3? 16 plus x plus 5, 25, right? So this is negative 25. The positive version is 25 over here. So you can do negation with just 2 operation, not n plus 1. Addition, again, is simple. In the unsigned addition, right? Unsigned addition, just add the 2 number. If you have carry bits, they will be thrown away if it overflow. Overflow means that let's say you want to add these 2 numbers together, right? This becomes what? 0, 0, 1, 1, 1, right? And let's say you only have 4 bits to store your data, right? The result would be 1, 1, 0, 0, and you throw away this 1 extra bit. This is called overflow. Sign addition is where you might want to be a little bit more careful. Sign addition, let's say A and B are integer. A plus B is you cast A and B as unsigned, so everything follow this rule. You add the 2 numbers together, you add the bits together, right? You add the bits together like this. And then you convert it back to an integer. So let's say these are the 2 numbers. The result is basically 1, 1, 0, 0, which is negative 4 plus 2. This is negative 2. If it's only up to 4 bits, right? So with that, it means that you can have overflow. You can have overflow where you add, let's say you add big positive number, something like 0, 1, 1, 0, something like this. Right? So let's say I have a character and I add this with this. What's the result? 0, 0, 0, 0, 1, 1, 0, 1. These become a negative number, right? So if you add 2 big positive number, it might result in a negative number if it overflow. Because it's a signed integer, it overflow into that signed bit. So it flips your result into a negative region. Some chip, some architecture actually allow special register. It allows you to tell, hey, something overflow here. Something might be wrong. Check that. Right? So some processor have that option. What about subtraction? Subtraction is simple if you know how to negate. You know how to add. Subtraction, for example, A minus B is the same as A plus negative B, right? Which is the same as A plus negation of b plus 1. So that's how we subtract. Any question here so far? Basically, subtract is negation plus 1 plus that number. Okay, so how do we multiply by the power of 2? Multiply by power of 2 is left shift, actually. Why? Let's say I have this number a. I do left shift by 2. Right? Let's look at this example. Let's say a is 0, 1, 1. So let's say that's our number. Right? What's the shift step? What will happen if I shift this by 2? This is 1, 1, 0, 0, 0. Oh, my bad. Too many 0. I shift everything by 2. This become 1, 1, 1, 1, 0, 0, 0, 0. Right? This is 2 to the 2, 2 to the 3, 2 to the 4, 2 to the 5, 2 to the 7, 2 to the 6, 2 to the 5, 2 to the 4, which means I can factor this out, right? This is 2 to the 2 multiplied by 2 to the 5 plus 2 to the 4 plus 2 to the 3 plus 2 to the 2, which is exactly the same number as this. This is A, right? So A shifted left by 2 is equal to A multiplied by 2 to the 2. So if I say A left shift by n, what's that equal to? Is A multiplied by what? It's multiplied by 2 to the n, right? So this is a good trick that is done all the time in your program. If the compiler see that you want to multiply by 4, it will do A left shift by 2. It's a lot faster. If you do multiply by 2 to the 8, it will do left shift by 3. If I have A multiplied by 7, sometimes the computer would actually do this. A left shifted by 3. And then do what? To make it 7. Right? So this is A left shifted by 3 minus A, right? You convert multiplication into left shift and subtraction. Left shift, subtraction, addition is faster than multiplication. So computer will do this for you all the time. All right, so you can do the same thing with the divide, right? A right shifted by 3 means that I want to do A divided by 8 or A divided by 2 to the 3. You have the unsigned version for the divide as well as the signed version. Signed version would be arithmetic. It would extend the most significant bits. Unsigned will not, but it would work both ways. It will work both ways, both signed and unsigned. If you do multiplication, it basically means that you multiply two numbers, which if you have n bits, it can produce 2n bits, which means it's likely that's a lot of time you multiply two number and they overflow. Make sure you are careful with that, right? If it go over the maximum value of an integer, make sure you cover that part, otherwise your program becomes buggy. You can do bit manipulation for many other things because of this reason. There's a kind of like established law that say if you can implement and or and not, you can implement any mathematical function. any mathematical function, which means that if you can have an or, and a not in your circuit, you can build a computer. Are you with me? If you can build an or and not, you can build any logic for the computer. In fact, if you just have a NAND gate or a NOR gate, you can build a computer. And this is actually how your computer is built. Right? It's a bunch of these logics string together, and now it can do fancy things. Machine learning, data analytics, data science, data engineering, a lot of cool things that pays a lot of money for all you who will graduate and work on those areas. Right? What does this mean for you? It means that you can use this logic operation, which is actually simple to do in a computer, to do many, many things. Here's one example. So I'm gonna leave about 5 to 10 minutes for you to think about the solution to this. So I have an array of integer. Let's say I have an array that say 2, 4, 3, 5, 3, 2, 5, right? This array is guaranteed that each integer will have its pair. You have 2 and 2, right? You have 4 and, well, that's one integer that doesn't have a pair. So in this case, 4 doesn't have a pair. There's 3 and 3, that's 5 and 5. And we want to identify what's that number with no pair. What's that number with no pair? How can I find this number? All right, so I'm gonna give you all 5 minutes to play around with this question a little bit and come up with a possible solution to find 4. You can turn on the microphone and discuss, chat on a chat, propose something. My hint, I can use logical operation on the elements of this to get that number. Not close enough, not and. I cannot use an and. What I want, right? Basically, what do I want is if there's a pair, if I do operation on that pair, let's say n doing something with n, I want that to be 0. I want to get rid of that. I want to get rid of all the pair, right? I'm alone. I'm jealous. I want to get rid of every pair that I see. What's that operation? That's X and is not an operation. Yes, exactly. Yeah. XOR, come to your rescue. Why? XOR is if you have 1 and 1, that's gone. If it's only 1 and 0, you still have the value. 0 and 1 is 1. 0 and 0 is 0, right? So that's XOR. It means that if I have a pair A and A, 0, A and 0, A, 0 and A, I got A, 0 and 0, I got 0, right? Which means that if I XOR everything here, what I will do here in this array, I'll just do 2 XOR 4, XOR 3, XOR 5, XOR 3, XOR 2, XOR 5, in any order, right? Okay, sure. Then don't kill me. I have my own pair. You can do it in any order, but eventually these two will get XOR out into 0. This 3 will get XOR out into 0. This 5 will get XOR out into 0. You get 4 XOR a bunch of 0, which is 4, right? So you can just XOR everything to identify that single number. All right, so this is just one trick that I'm not sure there might be some use in the real world. I got asked this question randomly when I was walking around in a job fair as a CMU student back like more than 10 years ago, and I cannot answer this question to be honest. So yeah, the solution is to loop and use XOR for all the elements, and you find that one number. But you can see, right, this logical operation can be useful because your obvious answer to this is, well, I guess you can sum every number together and so do some subtract, then you can extract the number. You can loop and do a set, right? And if there's a repeated element, yeah, you can try that. You have to if you have repeated element, you count it up and find the location that doesn't have the value two. There are many solutions for this problem, but one of the really fast solution is XOR. You loop XOR everything, you got the results, and it's actually really fast. And you can try this. So you can try this in the program, right? So that's it for today. Before we leave, make sure you are aware midterm cover up to now, up to like right now. We have in class exercise 5, which is we don't have time to migrate to Discord and do a Q&A. We'll just do a Q&A right now, right here until 4 o'clock. We have in class exercise 4 and 5 for you all to try. This will give you practice with the C language. Sorry for taking so much time. I did not intend for this lecture to go on for 2 hours. But hopefully things are more clear. And that's it for today's class. I'm going to do a Q&A. Any questions, just type it in or turn on the microphone and talk. If you don't have question, if you want to go to the next class, feel free to sign off and leave the meeting. All right?
อาจารย์ครับ
Yes.
I don't catch it, but when you take a break, I think someone asked you about the permission denied, right?
Yes.
I got the same error when I want to do the SCP command from like in class 2, and since we have to upload our files for assignment 1, I'm worried that I couldn't do it.
Yeah, so
And you
if,
mentioned
okay, let me put it this way. If ultimately you have a solution, but somehow you cannot manage to upload to the server, send me an email and submit that particular zip file on Canvas. All right?
okay ครับ
Yeah, so at least for assignment 1, and we'll make sure we figure this out before assignment 2 be ended, right? Just in case I wasn't able to like make it to the make office hour or get back to you by tomorrow and figure out what's wrong. There's a question out in class 4. The input will be line by line or multiple lines, whatever is convenient for you. I actually personally make it as convenient as possible to process the input. You can say, okay, if my input becomes stop, it will stop reading the input, or you can just use a file as an input. How do I know? How do I know if he know about the appointment? Oh, I'll brief him up. Basically, I'll brief him up because I'm meeting him in like 10 minutes actually. So I'll make sure I brief him up about this. Yeah, no problem. Any other questions? When is your midterm? So that is when is your midterm? Actually, we did establish that on Tuesday, I believe February 16th.